What does it take to build a structure capable of protecting thousands of lives beneath the ground during extreme disasters? From geotechnical investigations and deep excavation to reinforced concrete systems, waterproofing, and emergency life support infrastructure, this is the complete engineering process behind constructing a modern underground disaster relief shelter. The project begins with comprehensive site selection and feasibility assessment. Engineers evaluate terrain stability, accessibility, flood exposure, and seismic risk to identify the safest location for underground construction. Topographic surveys establish elevation profiles and natural drainage behavior across the site. Geotechnical investigations, including borehole drilling and laboratory testing, determine soil-bearing capacity and groundwater conditions. All collected data is integrated into engineering feasibility models to ensure long-term structural resilience and operational safety. Site preparation begins with clearing vegetation, debris, and unsuitable organic material from the construction zone. Grubbing operations remove buried roots and unstable surface layers that could cause future settlement issues. Heavy machinery reshapes the terrain to create a safe and uniform working platform for excavation activities. Materials are segregated for disposal, recycling, or reuse according to environmental management standards. Proper site preparation directly improves compaction performance, structural stability, and long-term foundation reliability. Excavation operations proceed to the required design depth to accommodate the underground shelter structure. Earthworks are carefully managed through coordinated cut and fill operations to optimize material handling efficiency. Stepped excavation slopes, retaining systems, and shoring supports maintain excavation stability and worker safety. Continuous surveying verifies alignment, depth, and dimensional accuracy throughout construction. The exposed subgrade is then prepared for foundation treatment and structural development. Subgrade preparation and compaction. Subgrade preparation establishes the primary load-bearing platform for the underground structure. Moisture conditioning is carefully controlled to achieve optimum compaction performance. Vibratory rollers compact soil layers to specified density requirements, minimizing future settlement risks. Field density testing verifies compliance with engineering specifications and quality control standards. Uniform compaction ensures stable load transfer and long-term structural performance. Geotextile and drainage installation. Geotextile systems are installed to provide soil separation, filtration, and long-term ground stabilization. Drainage networks are designed to control groundwater movement and prevent hydrostatic pressure buildup around the structure. Perforated pipes are installed at controlled gradients to ensure continuous water discharge. Granular drainage layers facilitate efficient subsurface flow and reduce moisture accumulation. This integrated drainage system significantly improves structural durability and waterproofing performance. Lean concrete blinding. Lean concrete blinding is placed to create a clean, level, and stable working surface for foundation construction. This layer prevents contamination between structural concrete and underlying soil materials. Uniform leveling improves dimensional control and reinforcement positioning accuracy. The blinding surface also protects foundation components during subsequent construction activities. It serves as the first engineered interface within the structural foundation system. Reinforcement and formwork installation. Structural reinforcement is installed according to detailed engineering design specifications. Rebar spacing, anchorage, and concrete cover are carefully maintained to ensure structural durability and strength. Heavy-duty formwork systems define the geometry and containment of the future concrete structure. Inspection teams verify dimensional accuracy and compliance before concrete placement begins. This stage is critical to the load-bearing capacity and resilience of the shelter facility. Foundation concrete pouring. High-strength structural concrete is poured continuously into the reinforced foundation system. Internal vibrators eliminate trapped air and ensure proper concrete consolidation around reinforcement steel. Precision finishing maintains level tolerances and surface uniformity across the slab. Batching plants monitor mix proportions to guarantee consistency, workability, and compressive strength. Controlled curing procedures begin immediately to achieve long-term structural performance. Reinforced concrete wall construction. Reinforced concrete walls form the primary structural enclosure of the underground shelter. Formwork systems maintain alignment, dimensional precision, and surface quality during concrete placement. Concrete is poured in controlled stages to ensure uniform consolidation and structural integrity. The walls are engineered to resist lateral earth pressure, groundwater forces, and external impact loads. Integrated waterproofing measures begin during wall construction to enhance long-term protection. Roof slab construction. The roof slab serves as the primary protective barrier above the underground facility. Structural reinforcement is designed to withstand overburden loads, external impact forces, and emergency conditions. Temporary formwork and scaffolding support the slab during concrete placement and curing. Concrete operations follow strict sequencing to maintain structural continuity and quality. The completed slab provides critical protection against external hazards and environmental exposure. Waterproofing and insulation. Waterproofing systems protect the underground structure from moisture infiltration and groundwater penetration. Bituminous membranes create continuous sealed barriers across external concrete surfaces. Thermal insulation layers regulate interior environmental conditions and improve operational efficiency. Special attention is given to joints, penetrations, and connection points to eliminate leakage risks. Long-term durability depends heavily on precise waterproofing installation and quality control. Backfilling and compaction. Backfilling operations are performed systematically using engineered fill materials surrounding the completed structure. Material placement occurs in controlled layers to maintain uniform compaction and structural stability. Each compacted layer is tested to verify density compliance with engineering specifications. Drainage pathways and waterproofing systems are protected throughout the filling process. Proper layered compaction minimizes settlement and preserves long-term structural integrity. Mechanical, electrical, and ventilation systems. Mechanical, electrical, and ventilation systems provide the operational backbone of the shelter facility. FAC systems maintain safe air quality and environmental control under confined underground conditions. Backup generators ensure uninterrupted emergency power during disaster scenarios. Integrated control systems manage lighting, communications, ventilation, and life support infrastructure. System redundancy is essential to guarantee operational reliability during critical emergencies. Interior finishing and safety systems. Interior finishing transforms the structure into a fully operational emergency shelter facility. Fire suppression systems, emergency lighting, and evacuation signage are integrated throughout the interior environment. Durable finishes are selected to withstand continuous use in emergency conditions. Space planning maximizes occupancy efficiency while maintaining safety and accessibility standards. Every component is designed to support occupant protection during disaster response operations. All structural, mechanical, and electrical systems undergo comprehensive testing and commissioning procedures. Pressure testing, ventilation analysis, and emergency simulations verify operational readiness under critical conditions. Engineers inspect every component to ensure compliance with safety and performance standards. Project documentation, operational manuals, and quality certifications are finalized for handover. The facility is officially approved and prepared for emergency deployment. This underground disaster relief shelter represents the integration of engineering precision, structural resilience, and emergency preparedness. Every structural layer is designed to withstand extreme environmental and disaster conditions. Integrated life support systems ensure continuous operation during critical emergencies. Advanced construction methodologies provide long-term durability, protection, and reliability. This is resilient infrastructure engineered to protect lives when disaster strikes.